Greetings to the respected faculty. I am Lasya Mandapati from CSC AI and ML B section. My roll number is 24951A6686, and today I'll be presenting my project titled Building an Arithmetic Expression Evaluator using Stack ADT in Java. This project focuses on applying the principles of data structures, particularly the stack abstract data type, to solve one of the most fundamental problems in computer science: evaluating arithmetic expressions. Over the next few minutes, I'll explain the motivation behind the project, the methodology I followed, the implementation in Java, and the results I achieved. Arithmetic expressions are at the heart of almost every computational process. Whenever we calculate something, whether it's a calculator, a compiler, or even in a spreadsheet, we're actually evaluating arithmetic expressions. The challenge is that different notations, infix, postfix, and prefix exist. All of these need to be handled correctly according to operator precedence and parentheses. Doing this manually or with poor logic can lead to incorrect results. Enter the stack ADT. The stack ADT offers a clean and efficient solution. It follows the last in first out principle, which matches the way arithmetic operations are nested and resolved. In this project, I built an evaluator in Java that can handle all three notation: infix, prefix, and postfix. Not only that, it can also compute the results accurately using stacks. The main problem I wanted to solve was that traditional evaluation methods often fail to handle complex expression with multiple levels of nesting or different operator precedence. So, the goal of this project was to design and implement a unified Java program that could 1. Convert infix expressions into postfix or prefix form using stack operations, and 2. Evaluate all types of expressions correctly. Essentially, I wanted to show how stack based algorithms can make complex algorithmic. How do I say this? I wanted to show how stack based algorithms can make complex arithmetic processing simple, structured, and reliable. The objectives of my project are quite straightforward. 1. To implement the core logic of the stack expression evaluation using stack ADT. 2. To support all three expression notations: infixed, postfix, and prefix. To ensure 3. To ensure accuracy by applying the correct precedence and associativity rules. And finally, to test multiple expressions to validate that the system works correctly and efficiently. By achieving these objectives, my project demonstrates how a simple data structure like a stack can be a powerful tool in real computational logic. Before we get into the algorithm, let's briefly review what a stack actually is. Well, a stack is a linear data structure that follows the last in first out principle, or LIFO for short. The main operations are, as you can see here, push, which inserts an element on top of the stack; pop, which removes the top element; and peek, which lets you see what's on the top without removing it. In the context of arithmetic expression, the stack is used to store operands and operators temporarily. When the right operator is encountered, we pop the necessary operands, perform the operation, and push the result back. The simple yet powerful behavior makes stack perfect for evaluating arithmetic expressions systematically. Now, coming to expression types, there are three main types of arithmetic expressions. The first one, infix, where the operator is between the operands, like a plus b or b plus c, or even simply c into d. Postfix, where the operator comes after the operands, like cd divide or de multiplication. Prefix, where the operator appears after the operands, before the operands, like minus ab, plus ab, or into ab. The infix expressions are easy for humans to read. but difficult for computers to evaluate because of the need to handle parentheses and precedence. That is why we convert infix expressions into postfix or prefix forms, which can be evaluated directly and unambiguously using the stacks. The methodology for this project followed a step by step algorithmic approach. First, the input expression is parsed and broken into tokens, numbers, operators, and parentheses. Next, we use one or two stacks to manage these tokens. For conversions, I implemented Dijitra's algorithm to convert infix to postfix. For evaluation, the algorithm pops operands and applies operators as it moves through the expression. The same logic works in reverse. We just process the expression from left to right. This modular structure ensures that each part of the process, conversion, evaluation, and display, works independently, but it also integrates seamlessly. Let us now take a look at the code. The project was implemented in Java using the built-in stack class from the java.util package. Here is the small snippet of the code, or at least the full code. If you look here, you can see where the case is plus, we push a plus b, and where the case is minus, we push a minus b, and so on. In detail, if it needs to be explained in detail, the program first converts the infix expression into postfix form using precedence rules, then evaluates it using a stack. It supports all the main arithmetic operators: addition, subtraction, multiplication, division, and exponentiation. This modular approach makes the program both easy to test and easy to extend in the future. Here's how an example of the program turned out. The input given was 3 plus 5 in parentheses times 2 to the power of 3 in parentheses minus 4. And as you can see, these are the expected outputs and results. Now let us also look at the actual output. This is the actual output we get from the model created. Now, the consistency of this model across all notations confirms that the logic is implemented correctly and that stack based computation is heavily reliable. From my observations during the testing, the stack ADT drastically simplified the handling of precedence and nesting. The program's modular design allowed it to handle multiple expression forms easily. The same approach can be expanded to include other mathematical operations. Most importantly, this project showed how theoretical data structure concepts directly translate into practical working solutions in programming. These insights reflect how foundational topics like stacks are essential to areas like compiler construction and expression parsing. Conclusion and future scope. When it comes to conclusion, this project successfully achieved its goal of creating a stack array based arithmetic expression evaluator in Java. It demonstrated how data structures can simplify complex computational tasks like parsing and evaluating expressions. The evaluator correctly processed infix, postfix, and prefix forms, proving both the correctness and flexibility of the design. Now, let us move on to future scope. In the future, the project can be extended in several ways. First, by adding more operators like modulus and trigonometric functions. Next, by improving error handling for invalid inputs. Third, by creating a graphical user interface for easier interaction. And also, it can even serve as a core module for compiler or interpreter systems, making it an excellent example of applied computational theory. Thank you for your attention. That concludes my presentation on building an arithmetic expression validated using StackADT in Java. This project helped me connect theoretical knowledge of data structures with real world programming language. Thank you again.